In this lesson, we'll begin our study of chemical kinetics. When we're studying kinetics, what we're looking at is how fast a particular reaction takes place. Our focus on thermodynamics is to determine whether or not a reaction can take place at all. And when we revisit thermodynamics after this particular chapter, you'll be able to see specifically how we use thermodynamics to do that. It's really important to consider both the thermodynamics and the kinetics of a particular reaction, because it's nice to know that a reaction takes place, but if it takes several days for the reaction to occur, then that's not going to be very useful. When we're studying kinetics, what we need to use is the rate of reaction. And the definition of rate of reaction is the change in concentration of a reactant or product with respect to time. So it's the change in the concentration as a function of time. So this is much like other relationships you've seen in physics, like the change in distance over time is the velocity, or the change in velocity over time is the acceleration. So really what we're looking at is the speed at which reactants are used up or products are formed during a chemical reaction. And there's different ways that we can monitor or measure the reaction rate. It really depends on the reactants and products in the system. For example, in this particular reaction of magnesium plus hydrochloric acid, we can use the mass, the pH, or the electrical conductivity in order to monitor the rate of the reaction. The reason that we can do this is because the gas is being produced, so the reactants over time are dropping in mass. So by monitoring the change in mass with respect to time, we can monitor how fast the reaction is proceeding. With pH, because HCl, or an acid, is one of our reactants, we can monitor the change in the pH as the hydrochloric acid is being consumed. The pH is giving us an indication of the concentration of the H+ in solution over time. Electrical conductivity can also be used, and it is measuring the amount of ions in solution. So in a case where there are different amounts of ions on either side of the reaction, so in this case we've got 2 moles of ions producing 3 moles of ions. So as this particular reaction proceeds, the number of ions in the solution is going to increase, and therefore the electrical conductivity will increase. So by monitoring that conductivity, we can monitor the rate of the reaction. We can also use pressure when there is a gas being produced in a reaction. So I can monitor the production of oxygen by the increase in pressure as a function of time. We can use color. So you've seen before how to use the spec-20s or the spectrophotometers or colorimeters, all of which measure the intensity of a particular color. And there's a relationship between the intensity of a color and its concentration. So if you have a colored product, you can monitor the addition of that colored product to the system. Or if you've got a colored reactant, you can monitor the disappearance of the color from the system. In a case where you've got gases being produced, you can also monitor the volume of a solution. So like with a baking soda vinegar experiment. Now when we're looking at rate of reaction, we do have a natural understanding of how we can make a reaction go faster. It comes from the fact that we know that for a reaction to happen, molecules need to collide with one another. So we're going to use more formally called the collision theory to help us to understand the rate of a reaction. We know that in order for a reaction to occur, they must collide with one another. The molecules must collide with one another. Looking further into this, we need to consider the fact that the collisions between the molecules actually need to be effective in order for the reaction to occur. So let's consider 2 scenarios. Let's consider changing the concentration of reactant molecules. If we change the concentration of reactant molecules by placing more of one reactant into the system, that naturally is going to increase the rate of the reaction if we use the collision theory, because we're going to increase the chances of collisions that we have. Increasing the surface area will do the same thing. Increasing the surface area is, for example, taking a large tablet and crushing it into smaller pieces. That makes more of the substance accessible, and therefore there's more chance for collisions, and the rate will naturally increase. Temperature is another thing to consider. Increasing the temperature naturally, in most cases, will increase the rate of the reaction. We're going to investigate these in a little bit more detail to really be able to articulate and understand why the rates of reaction are affected by these changes. And we're going to advance our discussion to think of the collisions as not only just simply occurring, but as being effective. And there are two things to consider when we discuss an effective collision. There is the orientation of the reactants, and there is the energy of the collision. We're going to look at these diagrams. They're potential energy diagrams, and these are simply an extension of your enthalpy diagrams. Okay, so let's look first at a regular enthalpy diagram. The enthalpy diagram simply shows you the change in energy of reactants and products. So in an exothermic reaction, you start with a certain amount of energy in your reactants, and overall the energy decreases, okay, and the excess energy is released. And we would draw an enthalpy diagram like so. If we expand this, okay, so we're looking at the reactants over here and the products over here, and consider the pathway of the reaction, we're going to get a potential energy diagram like this. Okay, so this is looking at the reaction over time. Now, what you'll notice is that there is this huge amount of energy. There's suddenly this potential energy increase before the products are actually formed. This is called the activation energy. This is the amount of energy that the reactants need in their collision in order to become products. And the reason for this is that in order for reactants to come into contact with one another, they need to overcome a significant amount of potential energy that's coming from the natural repulsions between the molecules themselves. So if two molecules collide and they've only got this amount of energy, then no reaction will actually occur. Okay? They might come near each other, but then they're going to repel one another and go on their merry way. So for a reaction to occur, we need for the combined collision energy to overcome what we call the activation barrier. Okay, so this is the amount of energy that the molecules need when they collide to actually form products. And it's called the activation energy. And we think of this as a barrier to forming products. At the peak, we have what's called the transition state. Okay, so this is the state where the molecules are nor reactants nor products. They're in a high energy state in between the two. And we'll look at an example in a moment. We can also look at a potential energy diagram for an endothermic process. So in an endothermic process, as you know, the reactants increase in energy overall as they form products. The activation energy is the difference between the reactants and the high energy state or the transition state of the reaction. And this is the amount of energy that the molecules need to bring into the collision in order to form products. If they don't have enough energy, then products won't be formed. Okay, so when we're talking about effective collisions, they need sufficient collision energy, and the molecules also need to be oriented properly. Let's look at, for example, a reaction between H2 and Cl2 to form 2HCl. In this reaction, we want to break the bond between H and H and between Cl and Cl, and we want to form bonds between two sets of HCl's. So this is an example of how these molecules should collide in order to successfully form products. Okay? As they approach one another, they go to the transition state, where we're in between the two states of reactants and products. These bonds aren't quite broken, these bonds aren't quite formed. So this is my high energy transition state. When the bonds are formally broken and formally formed, then we have our products of HCl. Okay, we've got two HCl molecules that go off in their own Now these two examples are examples of unsuccessful collisions, so they're not effective. If the H2 and the Cl2 collide side-on, we're not going to be able to form the products of 2HCl. Although in this case it appears like, okay, well maybe you could form a bond between this H and Cl. That's not good enough, because if this bond is formed and the Cl and the H are broken, okay, it's not necessarily the case that they're going to form products. Okay, so this is an example of an unsuccessful collision. Okay, the collision needs to be able to give rise to the appropriate transition state where we're in between forming and breaking bonds. If the chlorine and hydrogen collide on an angle, it's the same thing. Although this collision might allow the bond formation between this hydrogen and this chlorine, okay, this chlorine and hydrogen are left out, and therefore this reaction is not possible. So when we talk about effective collisions, we need to consider both the orientation and the amount of energy that the reactants and products that the reactants need in their collision. Okay, so let's look at how to draw some potential energy diagrams, taking into account the activation energy and the overall change in energy of the system. Okay, so in reaction 1, the change in energy is -10. Okay, that tells us that we've got an exothermic reaction with 10 kilojoules being released, and the activation energy for this is 15. So if I start at this amount, then this is going to be 15 kilojoules, okay? And I know the difference between the reactants and products is going to be 10. Okay, so this is 10, and this is 15 in this case. Okay, now keep in mind that this delta E is also the delta H for the reaction. And we're being proper by saying delta E because this is a potential energy curve. So in this second example, the activation energy is 25. So that's the difference between the amount of energy of the reactants and the amount of energy of the activated complex. So that's my EA. Okay, and then the change in energy overall is 15 in this case. Okay, and when we say reaction progress, okay, that could be monitoring the reaction over time. Okay, it's also possible for us to monitor, for example, the bond lengths of a particular reaction. So that's why we are a little bit general in our words there. In this third one, it's an endothermic reaction. So overall, the energy is increasing by 5 kilojoules. The activation energy is still the difference between the reactants and the activated complex. So this is still my activation energy, and this is still my delta E. Okay, now it is a bit of a challenge to label the y-axis here. okay, because we can't assign a 0 point. Okay, we don't know the actual initial amount of energy or the specific final amount of energy of the reactants or products. So that's why we can only show the changes, and we know that the difference between these 2 points is 10 and the difference between these 2 points is 15. Okay, we don't know the specific initial or final, okay, which is pretty standard for a potential energy curve. Now, we can use this information to decide which reaction is going to be the fastest. Okay? And if we look at them, it's the speed of the reaction is going to be decided based on the activation energy. Whether a reaction is endothermic or exothermic or releases a small or a large amount of energy doesn't matter. That's not what comes into play when we're considering the rate of the reaction. That would come into play in deciding whether or not a reaction can occur or is favorable. But when we want to consider the kinetics of the reaction or the speed, it's the activation energy that we want to consider, because the activation energy is telling us how much energy those molecules need for an effective collision. So the more energy they need, the less likely the reaction is going to occur quickly. So in this case, the reaction 2 is going to be the slowest in the forward direction. We can also look at the reverse of these reactions. Okay, so the reverse of this particular reaction has an activation energy of 35 because it's going from here all the way to the top. This one, the activation energy of the reverse reaction is 40 because it goes from here all the way to the top. And here it's only 15. Okay, so the third one is pretty quick on the reverse, and the second one is also still slow. Okay, collisions are important for the reaction, and having effective collisions with the right amount of energy is important. And using that information, we can explain the temperature effects on the rate of a reaction, being really articulate and scientific. Rather than just saying increasing the temperature is going to increase the rate, we can explain it in a little bit more detail. We know that the temperature gives us the average kinetic energy of the particles in the system. So what we want to do first, before we explain the effective temperature on the rate of the reaction, is we want to understand the relationship between the kinetic energy and the particles in the system. This is a graph that shows us the number of molecules with a certain amount of kinetic energy in the system. Even though we say that the temperature gives us the average kinetic energy, that doesn't mean that all of the particles in the system have a certain amount of energy. Okay? It tells us that there is an overall average, but that means that some of the particles are going to be moving faster, some of them are going to be moving slower, and a lot of them are going to be somewhere around the average. And this can be connected if you think about cars driving on the highway during rush hour. If you think about a given moment of time, there's going to be lots of cars driving some average speed. And then at that given moment, there might be a couple of cars who are almost stopped and a couple of cars who are going quite quickly. Okay? But overall, there's going to be a mixture of specific speeds with a bunch of people at the average. So this shows you at a specific energy, it tells you how many particles in that system will have that particular kinetic energy. Now, when we consider the rate of reaction, or how fast a reaction is going to go, we need to consider the effect of collisions. So if we put onto this graph the activation energy for a particular reaction, what we can see is that at a given moment of time, only a certain amount of particles have enough energy to overcome the activation barrier. So the majority of the molecules at this particular temperature for this particular example do not have the correct amount of energy in order to react. So what we want to do is look at what happens when we change the temperature. If you change the temperature of the system, what that's going to do is increase the average kinetic energy. So right now, the average is somewhere around here. With a distribution curve like this, if we increase the average, this is what's going to happen. The graph is going to get stretched out because just because we've increased the temperature, it doesn't mean that all of a sudden we don't have any molecules that are moving slow, which is what we would have if we simply moved this curve over, if we did a shift. So the area under the original curve is still going to be the same as the area under this new curve, okay? But it's kind of stretched out. So my average is somewhere higher, and it's somewhere around here right now. Now, if this is the case, the activation energy of this reaction hasn't changed. But what's happened is that increasing the temperature has simply increased the number of molecules with enough energy to overcome the activation barrier. So that's how temperature affects the rate of the reaction. Doesn't simply make it go faster, as it would be nice to just say. If we want to explain it quite scientifically, we need to say that increasing the temperature increases the average kinetic energy of the particles and increases the number of particles that have enough energy to overcome the activation barrier. And that's why it makes the reaction faster. More effective collisions is a faster rate of reaction. Now, because reaction rates are monitoring the concentration with respect to time, we can look at this graphically. If we look at this particular reaction of A molecules going to B molecules, we can monitor the number of molecules over time. So in the first 10 seconds, we've consumed 10 molecules of A, and we've produced 10 molecules of B, which reflects this 1-to-1 ratio that I have right now. Now, the rate of the reaction, or the change in concentration of the substance with respect to time, is actually going to be the slope at the of the tangent at a given moment of time. So if we want the rate of reaction, we need to take the slope of the tangent. Another thing to consider is what would happen if we changed the stoichiometry of the reaction. So if instead of producing 1 mole of B, we produced 2 moles of B. If that were the case, as 10 molecules of A were consumed, rather than making 10 molecules of B, we would make 20 molecules of B. So that's going to affect the steepness of the reaction. So in this case, B is being made at double the rate, or twice as fast. Okay, so if you look at the slope of the tangent here and the slope of the tangent there, okay, in the second example, it's going to be double. So just a couple of things to consider here. The rates of the reaction are going to reflect the stoichiometry, and the rate of the reaction, if you want the instantaneous rate of reaction, it's going to be the slope of a tangent at a given moment in time. Okay, this gives you specific rates, okay, for a specific reaction. It gives you the concentration and time. And what they did was found the slope of the tangent at given moments of time. And what you can see is that as time has progressed, you can see visually from the slopes and also with the values, the rate of the reaction actually decreases over time. Okay, so these aren't linear relationships. The rate of the reaction is going to decrease over time because as the reaction proceeds, the amount of reactant and product that you have is decreasing. So the number of effective collisions that you have is going to decrease as well. Okay, so it makes sense that the rate will decrease over time. What we want to be able to do, you want to be able to visually look at a graph and understand how the rates are connected to the slopes of the tangents. You're not necessarily going to need to calculate the rates of tangents, but understanding them overall is very helpful. More importantly, though, you need to understand that the rates of individual reactants and products are connected to their stoichiometry. Okay, so as you can appreciate, the products are always going to have a positive rate of reaction because their concentration is going to increase over time. And the reactants are going to have a negative rate of reaction because their concentrations are going to decrease over time. We're going to use the stoichiometry to relate the rates of one reactant to another or to a product. So let's look at an example here. We've got this reaction 4NO2 plus O2 going to 2N2O5. It says, suppose that at a particular moment during the reaction, the molecular oxygen is reacting at a rate of 0.024 mole per liter per second. Okay. So rate is the change in concentration over time. So that's why the units are molar per second, which is really the same as mole per liter per second. Okay, change in concentration as a function of time. When you know the rate of one particular substance, so in this case we know the rate that oxygen is reacting, 0.024, we can determine the rate of something else. So we can determine the rate of formation of N2O5. The ratio between these is 1 to 2. So N2O5 is going to be produced at double the rate that the oxygen is being consumed. So the rate is 0.048 mole per liter per second, or molar per second. The rate at which the NO2 is reacting is negative 0.096 mole per liter per second. It's got a negative rate because it's a reactant and it's being consumed, so its concentration is decreasing over time. And it's 4 times the rate of the oxygen being consumed because the ratio between them is 1 to 2. Okay, so let's look at one more example here. Molecular hydrogen is being consumed at a rate of 0.074 mole per liter per second. At what rate is the NH3 being formed? So we know the rate of the H2. We know that for every 3 H2 is used, we produce 2 NH3, and the rate reflects the same ratio. So applying the 3 to 2 ratio, okay, we find that the rate of production of NH3 is 0.049 mole per liter per second. Looking at the consumption of N2, it's reacting at a rate of 0.0247 mole per liter per second because the ratio between the nitrogen and the hydrogen is 1 to 3.